Hello everyone. In this session, let me continue one of the important theorem. If R and S are equivalence relation on a set A, then R union S infinity is a smallest equivalence relation on A, containing both R and S. It is one of the important theorem. It has been asked in one of the year. And this theorem is based on the connectivity relation. As you all familiar with the connectivity relation, I have done that in the previous session. Please go through that. Now, given that, before going to the proof of the theorem, let me revise one concept where I have discussed it in a closure of a relation. Fine. Suppose if a given a relation R, a closure of a relation will be A, A. Reflexive closure, right? So I'm talking about reflexive closure. Suppose if I have a relation R, then if by adding the elements like A, A to this relation will become a reflexive relation. So this relation will be a smallest relation. By adding this element will become the given relation reflexive. So we call this is a reflexive closure, right? Now we know that any relation on a set A is reflexive. So I am writing the same. We know that any relation on A given set A is reflexive only when if a relation contains an elements of the form say delta A is equal to A, A, and that element should be in the given set. Right? This is from the definition of reflexivity. For any set A is said to be reflexive only if it contains elements of the form A, A such that A belongs to a given set A, where delta A is a principal diagonal element, right? Principal diagonal element. Why? Because as you are familiar of constructing a matrix of relation, all the elements with reference to A, A will lie along a diagonal of a matrix, right? So I can write delta AR principal diagonal of a matrix A cross A. Fine. Now since R and S are in the question itself, in the theorem statement itself given, R and S are reflexive. If R and S are equivalence relation on a set A, we have to show that it is a smallest equivalence relation. When do we say equivalence relation? Meaning of equivalence relation is if it is reflexive, symmetric and transitive. So it is clearly given. Both R and S are equivalence. In the sense R and S are satisfying the condition reflexive, symmetric and transitive. So it is already clearly given. So I can write R is reflexive. It is given. R and S are reflexive. So R and S are reflexive, meaning is that in the relation both R and S there exists an element of the form A, A. Again A, A is an ordered pair which is in the set delta A. So I can clearly write this delta A will be contained in a relation R, also in relation S. Why? Because it is given that R and S are equivalence. In the sense it satisfies reflexive relation. So I can write delta A is subset of R and delta A is subset of S. Why? Because as the elements A and A will be present in both R and S. Further, I can write that delta A, since it is subset of R and S, so I can write it is subset of their union also as per the property of set. Further, what can I say is by the definition of connectivity relation, R union S is subset of R union S infinity, right? So I have already explained this concept. You just go through that. Fine. So I can write this for any relation R, I can write this by the connectivity relation, and this is from the above since delta A is subset of R and delta A is subset of S. Now let me combine these two equations. So from these two I can write delta A is also subset of R union S infinity. As this is subset of R union S, again R union S is subset of connectivity relation. So I can write delta A is contained in R union S infinity. Meaning is that, see here, delta A is subset of R because R is reflexive. Delta A is subset of S because S is reflexive. Now what I have arrived is delta A is subset of R union S infinity. So I can write R union S infinity is reflexive. Our aim is, see, I am going to repeat once again, given that R and S are equivalence relation, in the sense it is reflexive, symmetric and transitive, we have to prove that R union S infinity is also an equivalence relation. So what I have taken is given data I have taken, and I have proved that R union S infinity is reflexive. Now we have to prove for symmetric. Now it is also given that R and S are symmetric. Why? Because it is equivalence relation. So as per the symmetric condition, what I said, so suppose if R is a relation from A to B, that is an ordered pair AB exists, then BA should exist. In the sense R inverse from B to A should be there. Right? So I can write, since R and S are symmetric, I can write R is equal to R inverse. Why? Because in the relation R, the elements are in the form AB, whereas in relation R inverse, the elements are in the form BA. Similarly, I can write S is equal to S inverse. Fine. Now, since R is equal to R inverse and S is equal to S inverse, I can write R union S whole inverse as R inverse union S inverse whole inverse. Again, when you're going to simplify this, what you're going to get? R union S. Right? Now, so after simplifying this, you will get R union S. Meaning is that since R and S are symmetric, I can write R union S is also symmetric. Fine. Meaning is, suppose if an element ordered pair AB belongs to infinite connectivity relation, that is R union S infinity, then there will be a path from A to B. Meaning of AB is ordered pair AB is there exists a path from A to B in R union S. And we already proved that R union S is subset of R union S infinity as from the definition of connectivity relation I have used here also. So this is from connectivity relation. Since AB belongs to R union S infinity, and moreover meaning is that there exists a path from A to B in R union S. Moreover, R union S is further subset of R union S infinity. If there exists a path from A to B in R union S, then there should exist a path from B to F in R union S infinity. Right? So thereby I can write R union S infinity is symmetric. Fine. Now the last one is transitivity. So let me prove the transitivity. So for transitivity, no need to prove more. For transitivity, see here. Let me prove transitivity. I have already proved one theorem that R union S infinity is a transitive closure of it is a standard definition, closure of standard proved result. So if R union S infinity is another, then connectivity relation is always a transitive closure of R union S. Since R and S are already transitive, as in the given problem, they are equivalence relation, right? R and S are equivalence relation, meaning is they are transitive. So R and S are transitive. I can say R union S is also transitive. Further, R union S is subset of R union S whole infinity, right? As I already used this statement from the connectivity relation, I have used in all the three cases. So, if this was the case, I can say R union S infinity is also transitive. Remember, in this theorem, mainly we are going to use this concept, that is connectivity relation. So, this is what the proof is. Hope it is clear. If you want, I'll just recollect the concept. So, if it is reflexive, the elements A, A should be in the given relation. So, in the given theorem itself, it is given R and S are reflexive. So, what we have to prove is R union S whole infinity is also reflexive. If R and S are reflexive, as per that, their union is also reflexive. Moreover, union S is subset of R union S whole infinity. That is connectivity relation. This is I have already explained clearly in previous session. Please go through that. So by that I can say delta is also subset of R union S infinity. So that implies element AA will be in the set R union S infinity. Therefore, R union S infinity is reflexive. Now the same logic I have used to prove the symmetric and transitive as well. So you have to remember this concept of connectivity relation. Hope so it is clear. Now, the next theorem is based on poset. So, I have clearly explained the concept of poset in the previous class. Poset in the sense, what we say, a relation which satisfies, what we say, reflexive, antisymmetric and transitive. So, if all the three conditions satisfy, we say that as poset, and it is represented by A, less than or equal to within this type of bracket, right? So, that is what the poset is. Now, I have a theorem. If poset A and poset B, it is representation. If A and B are posets, then A cross B, Cartesian product of A and B, is a poset with partial order defined by AB is less than or equal to A dash B dash. In the sense, this is the condition to define a given relation. in such a way that A less than or equal to A in A and B less than or equal to B in B. Now coming to the proof, let me take any two element in proof. Let me take any two ordered pair of element in Cartesian product A cross B. Then what is the given condition is AB is less than or equal to A dash B dash. Further, A is less than or equal to A dash and B is less than or equal to B dash. This is what the given condition is for any pair of element in an ordered pair. Suppose if a particular number instead of A dash and B dash, if you are going to take A and B in A cross B, then this condition will holds good for this element as well. Then I can write AB is less than or equal to AB. Why? Because here I have taken an element A dash B dash, but here I have taken an ordered pair AB. So A dash B dash can be replaced by AB. Clear? So AB is less than or equal to AB in such a way that A is less than or equal to A in set A and B is less than or equal to B in set B. Clear? Why? Because since both A and B are posets, it is given in the theorem itself. Fine. If it is poset, then I can say it is reflexive. Reflexivity holds good, right? Holds for both A and B. Reflexivity holds for both the sets A and B. Now, for any ordered pair A comma B, which is less than or equal to A dash B dash, as per the condition, and let me take its complement, that is A dash B dash is less than or equal to AB. For both the elements, I am taking the given condition as in the theorem. So, if that was the case, I can say A and A dash are in set A and B and B dash are in set B. Fine. Now, further I can state that A is less than or equal to A dash and A dash is less than or equal to A. That implies, meaning is that, see, it is just a logic. You have to understand the concept. You can look at the theorem, that in the theorem itself it is clearly given, right? See here, this is the condition of if any ordered pair belongs to the poset, I can apply this condition and this condition, these two conditions. So what I have done is I have written the given statement as it is. Now what I am trying to do is I have considered two elements. It is something like AB and BA, its complement. So if I am going to consider two ordered pair in a particular relation, definitely that will satisfy the given condition, right? So that is what the theorem statement is. So I have applied the statement, I have rewrite the same thing. Now A is less than or equal to A dash when AB satisfying this condition. So that is what I have written. Fine. A and A dash are in A and B and B dash are in B. So if the A and A dash are in A, I can write A is less than or equal to A dash. And B and B dash are in B, I can write B is less than or equal to B dash, and moreover B dash is also less than or equal to B. Fine. This is one pair of element. This is one pair of element. I am applying the same property by taking first time ordered pair AB, second time I am going to take an ordered pair A dash B dash. I am applying for these elements the given condition this. Clear? I am applying this condition for the ordered pair AB first time, so I have obtained this condition, these two conditions. The second time I have taken this, so I have obtained these two. So this is one pair from the given definition and this is one pair from the given definition. Clear? Now from these two conditions, what I can say, see here, A is less than or equal to A dash is less than or equal to A. So these two concludes that A is equal to A dash. Clear? Now these two concludes that B is equal to B dash. So from these two I can say as A is poset. This is what the condition of poset is, right? So if you are going to take any ordered pair AB and A dash B dash, if they are equal, I can say they are satisfying a condition of antisymmetric property. So it is also given that A is a poset. So it is given in the question itself. A is a poset. B and B are posets. Clear? That implies I can write AB is equal to A dash B dash. From these two conditions I have written in a ordered pair. Clear? Now I have to prove a given poset is antisymmetric. First I have proved for reflexive. So AB is equal to A dash B dash I have proved. Next thing is I have to prove for it is antisymmetric. So as per the antisymmetric, let me take two ordered pair AB and A dash B dash. See, this concept I'm using again. Now you look at this step, you can understand clearly. I'm taking the ordered pair AB, right? Now applying the same definition. So when you're going to take AB, I can write which is less than or equal to A dash B dash. Now in place of AB, what I'm going to take? A dash B dash. So A dash is replaced by whole dash. So I can write here A double dash comma B double dash. Fine. Where A dash, A double dash, let me write A dash, A double dash will be in set A, and B dash, B double dash will be in set B. And further I can write the condition A is less than or equal to A dash and A dash is less than or equal to A double dash as per the given condition. I can write this. Similarly, I can write B is less than or equal to B dash and B dash is less than or equal to B double dash. By combining these two, I can write A is less than or equal to A double dash. See here, A is less than or equal to A dash. Again, A dash is less than or equal to A double dash. Something like a transitive property, I can cancel these two, so I am combining these two. Similarly, from this condition, I can write B is less than or equal to B double dash. Fine. The meaning of this above statement is that, in the sense, I can write the above statement, these two statements I can write as A comma B is less than or equal to A double dash comma B double dash. So this condition is satisfying, right? A less than or equal to condition is satisfying. But when we talk about usual antisymmetric, we should get equals here. But we are talking about a symmetric poset less than or equal to. So this condition is satisfying, right? See here, less than or equal to condition satisfying. AB is equal to, it is something like AB is equal to A dash, like BA. In place of B we have A double dash, in place of A we have B double dash. Clear? So this condition states that based on this condition we can say that it is antisymmetric. Fine. So I have already proved antisymmetric, right? So AB is equal to A dash B dash I have proved. See, what we say this property is transitivity. I forgot transitivity. Why? Because see, in the first problem what they have given, AB is less than or equal to A dash B dash. What we have proved is AB is less than or equal to A double dash B double dash. So these two elements are common, but by comparing the first, let me take this as equation 2 and let me take this as equation 3. By comparing equation 2 and 3, what we can say less than or equal to is transitivity. So as it satisfies reflexivity, symmetric and antisymmetric, I can say A cross B is equivalence relation, or else I can say poset, right? Since it is satisfying antisymmetric but not symmetric, poset. Or else I can say A cross B comma less than or equal to, it is standard representation, is poset. It might be somewhat confusing, but I'll send you the notes. You just go through the notes once, then you will understand well.